Just a short video here to explain the really interesting consequence of the physical properties of enantiomers. Okay, so in the last video we talked about naming enantiomers and how they're different compounds, they're non-superimposable mirror images. But what's really interesting about enantiomers is that they actually have almost all their physical properties are identical. So these are a pair of enantiomers that we've talked about earlier, right? Besides giving them two different names, how would we distinguish between these two compounds, which is very difficult because they have exact same melting point, exact same boiling point, the same polarity. They share most other physical properties. So a good question would be, how do we even know that these two compounds are different or that they're two different compounds? How could we isolate one from the other if they have the same boiling point? We couldn't distill them apart like we did in the lab. What we're going to find is that they share almost all the same physical properties, one of which that's different is the extent to which they rotate plane polarized light, which we're going to call optical activity, and I'll talk to you more about plane polarized light in a second. It was discovered about over 100 years ago by this guy with an awesome beard named Emil Fischer that chiral compounds, enantiomers, can rotate plane polarized light. And he discovered this with a compound that's produced by grapes and wine fermentation called tartaric acid. Notice that tartaric acid possesses two stereocenters. The mirror image of minus tartaric acid is plus tartaric acid. They're not superimposable. What he figured out, actually, looking through a microscope, he could see that there were two different crystal forms that were actually mirror images of one another. So he physically separated out those two crystals, dissolved them in water, and measured the extent to which they rotate plane polarized light. One rotated it in the positive direction, the other in the negative direction. So that was the first time that this was discovered. Let me explain to you what plane polarized light is. So remember from previous classes that light is a wave, and it's composed of an electric component and a magnetic component. This wave is actually oscillating not just in this direction, but also in this direction, and this direction, and this direction, and this direction. So we can be oscillating in all kinds of different directions in this one, or this one, or this one, or this one. But if we pass this through a filter, we can get rid of all the other directions and just have light that's polarized in one plane. So this we're going to call plane polarized light. Okay, so how do we measure optical activity? Optical activity is going to be a property of compounds that rotate plane polarized light. What we do is we take a sample and we put it in a polarimeter, and we put a sample inside the polarimeter inside of a polarimeter tube. We're going to do this in the lab. We take a light source, we pass it through a polarizer, so now it's plane polarized only in one direction. When it passes through that sample, it's going to rotate. It's going to rotate either clockwise or it's going to rotate counterclockwise. One direction is going to be positive rotation, one direction is going to be negative rotation. So notice that as the light passes through the sample, it's rotating the plane polarized light. So that plane, it's not the same plane that originally was in, that plane rotated. All chiral compounds have this property that they rotate plane polarized light, so we're going to call them optically active, meaning that they rotate plane polarized light. In contrast to that, non-chiral compounds do not rotate plane polarized light. So this instrument is called a polarimeter that we use to measure optical activity. Okay, so let's take these two compounds for example. We have R2-bromobutane and S2-bromobutane. This rotates plane polarized light counterclockwise direction. This rotates plane polarized light in the clockwise direction, 23 degrees. This one's minus 23 degrees. So we could also call this compound minus 2-bromobutane. The problem is we have to measure this first because there's no connection between R and S configuration and plus or minus. You just measure it. Sometimes R is plus, sometimes R is minus. In this particular case, the R enantiomer rotates in the negative direction, so it's a much more reliable naming method to give the actual configuration of the stereocenter. Notice that each enantiomer will rotate plane polarized light in an equal amount, but in opposite directions. So it's the same amount, 23 degrees in this direction, 23.1 degrees clockwise, 23.1 degrees counterclockwise. We said optical activity is a way that we describe a molecule that's chiral, or a molecule that is going to rotate plane polarized light. And if we took a one-to-one mixture of these two enantiomers, that's going to be called a racemic mixture, and that mixture will not rotate plane polarized light because the two directions will cancel each other out. So you'll see no optical activity from a racemic mixture or a one-to-one mixture of enantiomers. Okay, like I mentioned before, what you want to be careful of is that plus or minus describes the direction that a particular isomer or particular enantiomer rotates plane polarized light. It has nothing to do with RNS configuration, so please do not get those confused. So to summarize, it's important that you know that enantiomers have identical physical properties, except for one, that enantiomers are optically active, which means that they rotate plane polarized light. Each enantiomer is going to rotate plane polarized light in an equal amount, but just in an opposite direction. And remember, the definition of a racemic mixture is a one-to-one ratio of enantiomers that is optically inactive.